So, in digital circuits we mainly have gates. Okay. So, remember this is an AND gate, this is an AND gate, this is an OR gate, right, and this is an OR gate, and this is an XOR gate, and so on. Okay. And there is a NOT gate. Okay. So, these are the typical building blocks in a digital circuit. Okay. Usually these are implemented in CMOS, okay, complementary metal oxide semiconductor, complementary metal oxide semiconductor, or MOS. Okay. So, MOS stands for metal oxide semiconductor, right, and CMOS stands for complementary MOS. That means it includes both NMOS and PMOS transistors. Okay. So, this is a symbol for an NMOS transistor, and this is a symbol for a PMOS transistor. So, this is, let us say, the source and the drain, right, and this is the gate. So, the NMOS transistor acts as like a switch. Okay. When the gate to source voltage is more than what is called as a threshold voltage, the transistor turns on. That means it acts like a switch which is turned on. When VGS is less than VT, it turns off. Okay. So, it is a switch which can be turned on or off. The PMOS transistor is also a switch, except that it is if you take the NMOS transistor, right, when VGS is high, okay, that is if I apply a high voltage on VG, then it turns on. If I apply a 0 voltage on VG, it turns off. So, this is sort of just the opposite. Okay. So, applying logic 0 to VG turns the transistor on. Okay. Applying logic high to G turns it off. Okay. So, this can be understood with the example of an inverter. So, this is a CMOS inverter. So, if I apply logic 0 here, that means a voltage which is close to 0. Okay, close to ground, then this guy is going to turn off. Okay. So, the NMOS transistor cannot be conducting, whereas VDD the PMOS transistor turns on, okay, because applying a 0 voltage to G turns it on, and if there is a capacitance at the output of the gate, the capacitance will draw a charging current from VDD, right, and when it becomes close to VDD, okay, then this guy cannot conduct anymore, because this is already VDD and this is close to VDD. So, there is not enough voltage across the transistor. So, it will turn off, but effectively the capacitance became charged and as a result output became 1. Okay. So, a low here or a logic 0 here will cause the output to become 1, whereas if we did the other way around, suppose I apply a logic high, that means voltage very close to VDD, you will see that the voltage across, I mean the gate voltage for PMOS is high, therefore, this will turn off, whereas this guy will turn on. And if there is a capacitance here which has which is charged, okay, that will find a discharge path. Okay. So, soon the output will get discharged, the output capacitor will get discharged, and when output becomes close to 0, then this guy will not conduct anymore, because there is not enough voltage across drain and source. So, this will also turn off, okay, and the output became 0. So, here output is 0. So, you can see it is acting as an inverter. When A is high, output is 0, when A is low, output is 1. Okay. So, it is acting like an inverter. So, this is the CMOS inverter. Let us understand the NMOS. Let us similarly understand the NAND gate. Let us say 2 input NAND gate. So, let us say this is A and this is B, this is A and this is B. This is output. Okay. If A is 0, right, or B is 0, if A is 0, this transistor will turn on, if B is 0, this transistor will turn on. If both of them are 0, they will both turn on, right. So, as long as one of them is on, right, there is a charging path, okay, and if either of them is 0, there is one of these will be off, okay. If A is 0, this transistor is off, if B is 0, this transistor is off, if both of them are 0, both of them are off. In either case, if one of the circuits is 0, one of the inputs is 0, then you can think of this as a open, there is nothing, there is no way to conduct. So, if A is 0, the charging will happen. So, this may be the output capacitance that will get charged, and when it reaches close to VDD, this guy will turn off, okay, both of them will turn off. Okay. So, if you draw the truth table, if A is 0 or B is 0, in all these cases output will be 1. If both A and B are 1, okay, then both the PMOS transistor will be off and these guys will be on. Okay. If the output is charged to VDD, it will discharge and the output will go to 0. So, this is nothing but a NAND gate. So, if you look at the transistor a little bit more closely, So, there is an oxide layer and then there is polysilicon. So, these are the this is your gate. So, the gate is typically made of polysilicon and then there is a oxide which is a thin oxide, and this is a semiconductor material. Okay. So, this is the source and this is the drain. So, that is what we write as a transistor. So, this is the gate, this is the source and this is the drain. It is called metal oxide semiconductor because a long time ago I think this was made of metal, then there was oxide and there was semiconductor. Okay. So, this is an NMOS transistor. So, when you apply a high voltage here, a channel gets formed and conduction will occur. Okay. Whereas, when the input is 0, okay, then there is not much conduction, there is only minority carriers which are responsible for the current. A small current will flow if you apply a drain to source voltage, but it will not be such a large value because there are two diodes which are, see, this is there is a diode here, right. And there is another diode here and they are like connected like this. Okay. So, if you try to no matter whether you make this plus or minus or whether you make this minus or plus, one of the diodes will be reverse biased. So, as a result a very weak current will flow, that is the so called leakage current. Okay. But if you apply a high voltage here, then the channel will get formed here, okay, and that will lead to conduction between the source and drain. So, that is how this thing works. Okay. So, like I said long back this used to be metal, but now today it is mostly polysilicon, okay. But somehow the term metal oxide semiconductor has stuck. So, we still refer to it as MOS. Okay. All right.